All right. So what we learned, let me just, briefly go in within 5 minutes because those things are correlated. So as we spoke earlier, that the very first thing is in electrodynamics to understand about the electrostatics. And the next class, actually, I will, discuss Gauss law and how we can use divergences and all those things, So first of all, let me finish this electrostatic part today with the problem which I, um, stopped with for the surface charge and, uh, volume charge. Okay, so I will finish today this part. And then after, we will start divergence curl and electric potential, etc. in the next session. So before we go, let me just remind you what we have learned so far. So we learned that how principle of superposition could be used as a fundamental, to solve the fundamental problem of electrodynamics. And we learned that, principle of superposition basically added vectorially with respect to, the single charge and where we wanted to have the test charge to be affected. So this is one of the important thing. And on the basis of that, we solved some of the problems using the Coulomb's law. And we understand that sometimes we can use just the symmetry, and with symmetry, we can explain, some of the things like if you have, for example, 12 charges, then, what could be the field at the, center, etc. And we see that this is very beautifully explained. If we use, instead of 12 charges, if you use 13 charges, then the superposition principle is basically going to help us very nicely. And then on the basis of that Coulomb law, we also defined a quantity called the electric field. And electric field is simply the force which is equal to charge times electric field, or you can say the electric field is the Coulomb force divided by the test charge Q. Okay, and then after, again, this superposition principle we used, and we defined electric field which is dependent on the radial quantity, which is the distance, okay, from the source point and the field point. So this is a function of the position vector, and we're going to see today basically the application of this definition very nicely in terms of if we have a shell and we wanted to find electric field at some point, maybe let's say inside the shell and outside the shell, then what is going to happen, etc. We're going to see and realize this very beautifully today, the example which I'm going to discuss today. Okay, and by using this, then we try to calculate electric field at some distance point z. And in this configuration, we took that the z is basically the midpoint between two equal charges q, which is separated at a distance t. Okay, and then we learned that because of the individual charge, because this is just a discrete distribution of charges, so what we have to do according to the principle which we learned, that at any point where we wanted to find the electric field, we need to just use the superposition principle. So first of all, due to one charge, what is the field here? So since this is a vectorial quantity, so obviously we calculated electric field, for example, for this charge is E1, and similarly for the second charge, which is E2, and the direction will be radial as the definition says. Okay, and then after we saw that since both the charges are equal and all the distances which we measure like this are the equal, so the horizontal component cancel out and electric field is basically in the z direction. And then after we calculated that the total electric field due to these two charges with a given condition is going to give as Ez equal to 2 times 1 over 4 pi epsilon naught q over r square cos theta. So, and theta is defined like this. So here you can also define theta with respect to, x-axis, and you can convert this quantity according to the notations. This is not compulsion that one could only take this theta like, I have taken. But overall, the result will be unaffected because of these choices, because you need to at last you need to put everything in terms of the given quantities like d and z. Okay, so and then after one can also assume that if z is too large, that means z is too far from these two charges, then this could be seems to be like charge 2q, and that will called as a total charge of a system, and then the electric field definition is going to regain their definition accordingly. Okay, and so one of the application we can see that if we change this one of the charge to be negative charge, then what is going to happen? So this will make a dipole. Okay, and then we saw that due to the dipole, we know that if it is a negative charge, then electric field will be inside, and therefore only horizontal component basically play a role, comparing to what we did for two positive charges where only the vertical component adds up. Okay, and then we calculated this all things and regain everything down there. Then after I introduced something called because this was all like discrete charge distribution, but sometime or in general we can find we can see that there could be a distribution of charges in a wire or in a surface or kind of volume. So we started some problem making for this line charge distribution, where we denoted this line charge as lambda, and this is nothing but charge per unit length. Similarly, for the surface charge, we denoted it by sigma, and sigma is defined as charge per unit area. Okay, and for the volume charge, we define it as a rho, and we're going to see these two applications today, and then we will see that how these applications are very important when we start with discrete charge, then line charges, and how they are correlated to each other. And then after, in the last session, we discussed about this in a little bit detail, where electric field is basically transformed in terms of the charge densities, which we define as line charge, surface charge, and volume charge. Okay, and therefore we can say that this Qi and this summation over Qi is basically converted towards the integral part, and similarly distance should be, what we did here, like for I equal to 1, we have one thing, then plus 2, 3 like this. So now this is basically going to be integrated. And accordingly, then we define dq equal to lambda dl prime, dq as sigma dA prime. One can also remove this prime, but since I'm following one book, so the notation I wanted to just be, consistent with the book, etc. So, and similarly for the volume, this is rho d tau, where d tau is the 3 dimensions. So you can say in the Cartesian coordinate system, this d tau is basically dx times dy times dz. However, dA is just dx times dy, or you can say dy times dz, or dy or dz times dx, something like this. Okay. So this we already discussed in a detail. And then after, if I substitute these values in the electric field definition, then we can write for the line charge something like this, where ER is equal to 1 over 4 pi epsilon naught integral of lambda r prime divided by r square r cap dl prime. Similarly for the surface charge and volume charge. Okay, and then we use one application of this formula where now the electric field, we wanted to find the electric field if the charge is distributed, in terms of a line charge with a length, suppose it is 2L. Okay, and we wanted to have again, as we did in the discrete charge, that we have a discrete charge q, distance d apart. Here we take a line charge, and we wanted to find electric field in the middle of this, where the distance is given as z. Okay, so here we have to just use the same thing and integrate over 0 to L. Or what we can do, we can use the generalized definition, which I just discussed, and then substitute everything, because we know what is our vector, which is our prime vector, which is dl prime in terms of the one-dimensional object. So, and then substitute the values, and you're going to get the electric field very easily. And this is recommendable to use this kind of generalized formula, because this is going to be, useful for all of the applications which we, read or discuss further. Okay, so after substituting all those things, since already this has been discussed in horrible detail, so I'll just show up that this electric field is given in terms of the line charge lambda, like this expression. And again, we try to discuss in the limit when z is very, z is basically very far apart from the line charge, then this expression is basically written in terms of the simple charge divided by the distance square, right? So these are the things which we discussed. And also, if L is very infinite, like your line charge is very, very, long, or you wanted to measure the electric field near to the line charge, then this is reduced to this expression. So these are very important, formula which one should understand in terms of the physics as well. And therefore, we move towards another applications, and I basically gave you this kind of homework, which you can also, reproduce by yourself, where I gave all the hints that if line charge is like this and you wanted to find, electric field at one of the corners, okay, then we can use simply again some dx here, and put the distance like r here, and use the same formulation which I did before, like a generalized expression. And then we wanted to get something like this, and electric field is given by this expression. Similarly, if we have something like, a square with the length a, all the sides having the length a, and we wanted to find, at this point p, the effect of these line charges as an electric field here, then what we need to do, we need to just use this expression and put L equal to A over 2, Z equal to this, and then, you're going to get the electric field. So you see how these are the things which are correlated with each other. And similarly, if this square box is not, this square is not a square, but a circle, then we use again this expression, and we have to just use something like this expression, and you can put lambda times 2 pi r times z, etc. Now, the application, as we see that from one line charge, how one can get the electric field with these configuration. Now I left with these two examples, which I wanted to discuss today. That let's suppose now we have a disk like this, and the surface charge is given as sigma. Then what could be the electric field at point P, okay, which is a distance z from the center, and radius is given as r, okay. And similarly, we wanted to find a three-dimensional object. Let's suppose it could be a shell or it could be a sphere. Then because of this, what could be the electric field at point P, okay. So we're going to discuss these two problems today, which is, very important for understanding of electrostatics, which we discussed so far. And then after, in the next lecture, in the next session, we will discuss about the Gauss law, and we'll try to see that problem like this, which is really complicated if we use the generalized formulation which we used, can be reduced with respect to some mathematical quantity which we discussed, like a divergence and curl. And those laws are basically Gauss law, Stokes law, etc. Will help to solve this kind of problem very easily. Okay, so we will see this, maybe in the next session. But today we'll see this as a complicated way of solving the problems, and these are very important, to understand not only the concept, but also for any exam, whether it is your college exam or you are sitting in a competition. This is going to be very important. So far till now, I just revised what I have done. Do people have any question till now?
No, sir.
Okay, great. So let me move, and we're going to use the application of, as we had used, like we have a single line charge, and then we draw simple things. Like if we have a line charge, in the previous slide I show that if it is a square, then how we going to use the single line charge. I mean, first of all, you have a discrete charge, then that is going to be generalized for the line charge. And now we're going to see that if we have this kind of line charge distribution, then how this problem or this solution is basically going to use for the surface one. Okay, so let me make the slides in the presentation mode. I hope you can see this slide. Yeah, so yes, very good. So now the question is now written as like this. So it says that find the electric field a distance z above the center of a flat circular disk of radius r that carries a uniform surface charge sigma. Okay, so now this is a plate. Okay, and the charge is distributed among the whole surface. So now we have to find the electric field at point P. Similarly, as we did before, that we have to use the formula of the generalized electric field and try to find that in the limit of R, if it goes to infinite, then what could be the situation, and if Z is more higher than R, then what could be the So one can assume that if Z is too large comparing to R, that means it should appear as a point charge or something like this. Okay, but if R is infinite and you are just measuring, for example, your Z is near to this, then what is going to happen? Okay, so what we have to do basically to solve this kind of problem, first of all, one need to just make this piecewise. So let's suppose this is a plate. So what we can do, so with some radius r, let's suppose this is a small r, we can draw a simple surface like this. Okay, and then we will take a thickness, let's suppose this is dr along this. Okay, so and this distance is basically dr. Okay, so first of all we have to do this, and then we can see that this is just the example which we discussed in the previous slide, that if it is a ring, then we can suppose that this is this plate is basically made up of this kind of ring. So if I able to find the electric field because of this ring at point P, then we can just integrate these all rings where R should go from 0 to R, and then we can find the electric field very easily. Okay, so this is the concept here, which you might have used in mathematics sometime. Those mathematical thing is basically going to help us to do this. So what we did, we break the disk into rings of radius r with thickness dr, as I had shown here. Okay, so overall, I mean, let's try to see that this is something like this, which we already calculated in a previous slide. Okay, so another thing is that here we saw that this ring is basically dependent on lambda. Okay, because lambda is the line charge. So we have to convert this charge in terms of the surface charge. Okay, and we know that lambda is nothing but charge per unit length. However, surface charge is charge per unit the area. Okay, so the area of this ring with the thickness of dr, how are we going to find? So 2 pi r, we know that this is the perimeter and thickness is dr. So if I multiply this 2 pi r with this thickness, the area is going to be easily, easily recognizable. So the total charge is then defined as sigma times 2 pi r times dr, okay, which we can write simply as lambda times 2 pi r, and or we can say that lambda should be substituted in the expression of ring as sigma times dr, which is very easy to recognize from here, right? Because again, if I repeat, what is going to happen if lambda is basically what? Lambda is charge per unit length. So for this ring, we have a q divided by 2 pi r, because we know that this ring length is nothing but the perimeter of this circle. Okay. However, if it is a surface charge, then in terms of surface charge, we know that sigma is defined as q divided by the area. Now the area is basically for this ring which we obtained here is obviously the surface 2 pi r times dr. Okay, so therefore we can say that sigma times 2 pi r times dr is equal to lambda times 2 pi r. So this is consistent, and therefore from here we can find lambda. So lambda is given as sigma times dr, which is simply in terms of the line charge. Okay, and now we can use simply what we did in a previous slide, that for ring, the electric field is given at point P with a distance z, and radius r is given as 1 over 4 pi epsilon naught lambda times 2 pi r times z divided by r square plus z square over 3 over 2 and z cap. Okay, so what we have to do here, you understand very clearly that now lambda we know, so we can put sigma times dr instead of lambda, and then integrate over from 0 to r. Okay, so now problem is going to be very simple. So substitute this value. So E ring is given as now this, because I substituted instead of lambda, I substituted is sigma times dr, and then all expressions are same. So it is 2 pi r times z, and you can see in the denominator also expressions are same. Okay, so this will ease our problem. And so E ring, which we considered here, which I draw as a red line, we can calculate, we know electric field from the previous example. So now we have to integrate it. So here up to the boundary. Okay, so that's why I didn't write it here. But here the boundary, we know that this radius r is basically, if I go from 0, then maximum is the r. So what we can do, we can have the maximum range to be r here. Okay, and we know the variables. So here the variables is simply one variable, which is r, because z is not varying, z is constant. Sigma is not varying because Sometimes it could also happen that this sigma is basically the function of r. Then in that case, we could not keep out the sigma out of the integral. Rather, we should put the sigma inside. Okay, but here sigma is given as constant, so we can obviously take it out. 2 pi is also constant. 1 by 4 pi epsilon naught is constant. So the only variable is this r, which should be integrated from 0 to r, capital R. So we have to just do this integration. Okay, and this integration is easy to do. So after, you can put r square plus z square equal to some quantity, and then 2r dr is equal to that quantity du, and you just substitute r dr equal to that quantity, and it is going to reduce as this. Okay, which is very simple to understand. So by having this, and then you have to substitute the values. So initial value is 0, final value is r. So once you substitute this, you're going to get the electric field of a disk very easily. Okay. So I hope there is no question in between. If you have a question, you always interrupt me, and I will try to explain it again. Okay. So this is the electric field due to the disk, which we can, very easily calculate if we already go through, things like 1 by 1, which I showed as a revision. Now the question is, what is going to happen if I take the limit r to be infinite? That means either you can see that this P point, the point P, is very near to the disk, or you can say that this, this plate is, or the disk is very, very large, where we wanted to, comparing to this jet. Okay, so what is going to happen? I mean, this is simple mathematics which we can do from here. So if r is infinite and this is in denominator, so what is going to happen? This term is going to be 0. Okay, because 1 by infinite is 0, So we left with only this first term. So if I write this 1 over 4 pi epsilon naught 2 pi sigma z times 1 over z and z cap, because this term is going to be 0 for r tends to infinite. So this is nothing but sigma over 2 epsilon naught z cap. Okay, so these expressions are going to be very helpful once we discuss the Gauss law, etc., and we're going to use it very frequently without deriving these quantities. Okay, but one should have expertise in such situation as well. Now one can also get very easily the second condition, where if z is very large compared to the radius of this disk. So what we have to do here, since z is very large, so one can just substitute this, because obviously this is 1 over z, so we cannot play any significant assumption for this, but for this we can do this. So for that, what we can do, we can just use the binomial expansion, and we know that 1 over root over r square plus z square can be written as, I mean, if I keep z outside, then z square is basically, when you take from square root, it could be like simply z, and then is going to be 1 plus r square over z square. Okay, so and then if I take this denominator as a numerator, then it is going to have the power of minus half, and then just use the binomial expansion up to the first order, and by assuming that we can approximate that this is nothing but minus half times r square over z square. If you remember your binomial expansion, which you may have learned in your 11-12 classes. Okay, and then one could write, yeah.
So in the last case also we are finding E means we are finding E only, no sir?
Yeah, only electric field, yes.
Then sir, where is 1 by 4 pi epsilon?
So I'm just I am calculating this now. Okay.
Oh, okay, sir. Okay, sir.
Yeah,
Yes.
yeah. It is just
Mhm.
like I am
Yes.
just giving you a mathematical feeling that where this z, if z is very large comparing to r, then what is going to happen with this term only? Okay. So I'm just
Yes.
deriving this term like this. Okay. Now I'm going to substitute this in this expression. Okay. So if I now substitute this expression, then what is going to happen? So this is 1 over z already there, minus of 1 over z, and since minus is there, so minus minus plus 1 over 2 r square by z cube. So 1 over z is going to cancel, and then we left with positive half r square by z cube. Now we substitute this here. Okay, now this is clear. Yeah.
Yes, sir. Yes, sir.
Good. So now electric field of this disk is going to give us 1 over 4 pi epsilon naught. So 2 pi r square sigma divided by 2z square. Okay, I just combined everything, and then wrote it like this one. So because now this z is cancelled out with one of the z here, so that's why this is z square, and r square is already there, so r square should be substituted there. So what you can see here, so now you see this is a kind of magic now. So the moment you are calculating z from far apart from the disk, then it is simply the electric field definition for a single charge, right? Where the single charge is nothing, but this is pi r squared times sigma, right? And sigma, is the surface charge. And we have already defined that this is nothing but q, sigma is q over 2 pi r dr. So if I go for the whole disk, then this is nothing but 2 pi, the pi r squared term, which is going to come out. Okay. So these are, so, that's the physics that one needs to understand apart from the mathematics, how electric field is basically dependent, or the definition which we derived, we showed that electric field is a function of the position vectors, or you can say that where we basically calculating the electric field from the charge is very important here. Okay, so this will complete this problem, but if you have any question, obviously we can come back again on this. So you can see how this discrete charge expressions are going to use for the line charges, and then we saw that how this is going to use for the surface charges accordingly. Okay. Now the next thing is that, which I showed before, that you have given something like this, which is kind of a shell. Okay, so this is shell. That means inside it's a blank, just like air field or something. And this is just a shell with radius r. So let me read the question so that everything will be clarified. It says that find the electric field at distance z from the center of a spherical surface of radius r that carries a uniform charge density sigma. So this is the shell surface, or you can say spherical surface. Okay, and we wanted to find at some point P, which is z distance from the center of this shell, and this cell uniform charge density is distributed as a sigma. Okay, so this is not yet like a volume charge, it is just like a shell. Okay, and similarly then we have to treat the cases something like z less than r, which is inside. Somewhere here I wanted to calculate the electric field, and what is going to happen. Similarly, we wanted to find that what is going to happen if z greater than r, that is outside. And we can then express our answer in terms of the total charge q on the surface. Okay, so these are the given thing. Now we will use again the previous concept which we learned here. So what we do here, we wanted to use a spherical polar coordinate system, which you people are familiar with. So I will not discuss in detail of what spherical polar coordinates are You might know about these azimuthal angle and polar coordinates, etc. So we are going to just use that thing here. So accordingly, let's suppose that we have a element of surface charge to be taken, something like this. Okay, this is a surface charge, which is obviously on the surface. So that's why the radius is capital R, which is given already. And this is making angle theta. Now we have to actually express few things in some different angles, etc. So, we take this angle as a sigma, psi, and this angle as a phi. Okay. So, and we suppose that this is x-axis, this is y-axis, z-axis, as it is given here. So clearly here, one thing is that electric field is going to be in the z direction, as we had already seen. That let's suppose again, because that's why I actually revised the concept as well. Let's suppose there is a charge q here exists, and so symmetrically we can also see that some charge q is existed here, because this charge is distributed completely on the surface, right? So we can see that since these are equal charges, okay, so electric field is automatically going to be z, because x components are going to be cancel out, or I can say the y components are also going to cancel out. Okay, so automatically we know that what could be the direction of the electric field at point P. Okay, so the very first concept is that. Then we wanted to use some of the formula which we already learned, and according to our convention we always take this angle into consideration, which I mentioned today also before, that this convention of taking angle is going to help us the expression which we derived before. Okay, so in terms of this angle psi, we can write this electric field Ez equal to 1 over 4 pi epsilon naught integral dq over r square cos psi. Okay, because we just I had shown in the previous slides this expression. Okay, so now what are the quantities which are unknown? Because it clearly says that we have to express everything in terms of z, sigma, capital R, and at last the total charge q. Okay, so we have to find basically all those things in terms of the known quantities. Okay, so what do we have to do? So first of all, dq. So we derived this dq in a previous disk. We found that dA is nothing but 2 pi r times dr. Okay, but here this is now a spherical polar coordinate. So spherically, when we have this, the surface area is going to give you a r squared sine theta d theta d phi. So basically this is nothing but r d theta times r sine theta times d phi. Okay, so I mean, obviously in mathematical classes, if you have a doubt, I mean, you can ask there. So overall, this dA is nothing but r squared sine theta d theta d phi. Okay, so this is dq. The expression of dq we know. Okay, now unknown quantity is cos psi, and obviously we need to find this r squared as well. Okay, which is this r, basically in this PowerPoint mathematical expression is not shown like this. So you assume that this r is nothing but this r. Okay, so let's do some mathematics here. So from this from the cosine law, we can find this r very easily. So this r, let me also put this as so that you could not have a confusion. This r is nothing but this r. Okay, so you can write with this triangle and use the cosine law, and you can say that r square is given as r square plus z square plus 2rz cos theta. Okay, in terms of this angle is given here. So that's why we have to find things in terms of whatever given. So this is done. So R square we found. Now dq also found. Now we have to see cos psi. So from this, this triangle, we can find cos psi very easily. And cos psi is given as z minus r cos theta divided by r. So how we can do this? So you can see here, if I draw this perpendicular line over this z axis, then this distance is nothing but r cos theta, because you see this is perpendicular, right? In this triangle, in front of this theta, whatever line is that is called perpendicular. So this is base. So this distance from here to here is nothing but r cos theta. Okay, so this is r cos theta. And in this triangle, we wanted to find cos psi. So what we have to do, cos psi is given as, again, this is the base, because this is a perpendicular here. So this is the base. So this is nothing but, because this is total from origin to this point, the distance is z. So I have to just subtract this distance, okay, for this triangle. So this is going to give us z minus r cos theta divided by this quantity, which is r. Okay, so we can substitute here, and then cos psi is basically nothing but z minus r cos theta divided by r. So if I substitute here, so we can say that this is z minus r cos theta divided by r. That means r times r square is r cube. Okay, and r we know, dq we know. So next step is to substitute all this value. Okay, so after substituting, what we're going to get? So 1/4 pi epsilon naught dq, we calculated sigma r square sin theta d theta d phi divided by r square, which is this one, and then cos psi, which is z minus r cos theta by r. And r we can substitute from here again, which is going to be root over r square plus z square minus 2r z cos theta, or denominator can be written as this over 3/2. Okay, so let me do that. And yeah, one more thing which is important, that d phi, when you integrate it, this d phi, that means you have to integrate the overall cycle, then this is nothing but this is 2 pi. Okay, so we can just take it out, because, and other functions are not dependent on phi, so we can do this integral very easily. As you know that this kind of integral can be done with the 3 steps, right? So one is the integral over, rather we can say here we have 2 variables. One is the theta, one is the phi. Okay, so one has to do integral over theta and integral over d phi, and we know that d phi, by symmetry of this spherical coordinate system, we say that d phi is 2 pi, so we can always integrate it out, and then after the integration will be left out with respect to theta only. Okay, so let's substitute that. So after substituting that and everything, this d phi is going to give you 2 pi. So 2 pi we can come out from here, and then sigma r square, again sigma is constant, r square is constant, so we can take it out, and then under the integral we left with z minus r cos theta, which is here, sin theta d theta divided by r square plus z square minus 2r z cos theta 3/2. This 3/2 comes from, you can understand here that this is r, so this is of the power half of this quantity. So power half plus power 1 is going to give you 3/2 here. Okay, now the question is how to integrate it. So I'm just going to give you some hint here, and then in your pen and paper, you try to do it by yourself. However, everything is, I'm going to give you all the ingredient of this. Okay, so to do this integration, what we need to do, we need to just substitute cos theta, because cos theta is here in the denominator as well as in the numerator. Sin theta d theta is given, so always one can substitute cos theta as some quantity, let's say u, then du is going to give you minus sine theta d theta, so that you can eliminate this sine theta d theta in terms of du only. Okay. Also, it is very important that one has to have the limits. So we know that theta in the spherical polar coordinate, this angle theta is nothing but it could vary from 0 to pi only, because this is z-axis, right? So it will start from here and it will go up to this. So only 180 degree, there is you might have learned in spherical polar coordinate what is the range of this theta, and this range is nothing but 0 to pi. Okay. As phi is 0 to 2 pi, theta only moves from 0 to pi. Okay. So within this range, one has to find the limit on the basis of this transformation. So if theta is 0, then u is going to give you +1, and if theta is pi, then u is going to have -1. As you know that cos 0 is +1 and cos pi is -1. Okay, so the limit is going to change like this. Okay, so after substituting this all, what you can do now, this integral basically, if I suppose to have integration over theta, then obviously one can substitute this integral limits where it could go from 0 to pi, and if I transform it in terms of some quantity u, then the limit is going to have now this is +1, because 0 refers to +1 and pi refers to -1. Okay, so this way you have to do the integration now, which could be very easy, which you can do very easily like a partial fraction. So in partial fraction, if I use this quantity, then you can write the denominator in terms of 2 terms, which is going to cancel out, and then you can do this integration very easily. So just use partial fraction or whatever easiest formula and then you're going to get this integration done, and the final form should be represented in terms of these expressions. Okay, so this is going to give you, so this is just kind of your homework, which you can do very easily, and again I'm just saying that in case there is a problem, obviously you can ask me over email or in the next session. Okay, so just do this integration and you will find you should have, actually you must have find this kind of expression for the electric field. Okay, so this is, you can see how difficult is the mathematical formulation if I wanted to find this, if things are getting complicated like this. So that's why we have to formulate something which should generalize this concept in a very physical manner, and in the next session basically we're going to use that. But anyway, let me finish it first and then we will discuss those things later. All right, so what we found here, are there any questions?
Sir.
Yeah.
Sir, du equal to minus sine theta d theta.
Yes.
Then, sir, where is the minus sign?
So you can just probably what I did, I integrated over -1 to +1. Okay, so let me do this. So what you can do here basically, probably I forgot to mention this. You can always digest this minus sign because you have substituted the values here, cos theta as u. So you can put z minus ru, and then sine theta d theta is minus du. Okay, so this minus sign can be flipped if I wanted to have the limits from -1 to +1. Is it clear now?
Yes, sir. Thank you.
Okay, good. Very good. Okay, then yeah, so then let me write this whole thing all together and try to make it in a very simple form. So Ez is now, this expression, and then, you calculate this minus minus plus. So you can have this value of this. So now we have to work out for these cases inside and outside. Okay. And we have to finally express the terms in terms of the total charge Q of the sphere. Okay. So what one can do here, Z less than R. So can anybody guess what is going to happen? Or there is no need to guess, actually. You can just, you have the expression here, and you can find very easily. What is going to happen if Z is less than R? That means some point is inside the shell. Okay. Inside this spherical shell. Okay. What is going to happen?
Sir, we can neglect Z.
Are you sure? I mean, why one should neglect Z?
Oh,
I mean,
sorry,
because Z is
yes,
not two less, right? I mean, Z is
yes, sir,
Z
sir.
and R is not two less, right? You
Yes.
understand my point?
Yes, sir.
If I say at the center, then you can put like 0. Okay. But we are not saying that it is at the center. I mean, it is just somewhere inside this. So this modulus sign is very important here. So now consider if Z is less than R, then what is going to happen for this modulus sign, and what about the numerator? So any quantity which is less than R, this is going to give you a negative sign here. Okay. And here, obviously, this is modulus. So obviously, Z minus R is going to be like some positive quantity. And also assume that what is going to happen here. I mean, you can just substitute some value, So let me just fill it up and try to understand what is going to happen inside this. So you're going to get this as equal to 0. The reason is very clear from here, that 1 is the negative sign and 1 is the positive sign in the numerator. You understand my point? So this is going to cancel out, because obviously this is a modulus, so these quantities are same, but this quantity is positive and this quantity is negative, and they are equal. So by intuition itself, you can say that there is no charge inside this shell. Okay. And therefore, the electric field is going to be 0. Is it clear? That point is clear? Yeah.
Sir, can you repeat what you said?
Yeah. What I am saying here, if Z is less than R, let's suppose this value is something like R over 2. What is going to happen? Let's calculate it. Okay. So let's suppose Z is R over 2. So what this quantity is going to have? So this Z minus R is basically R over 2. That means this is going to have minus R over 2. Okay. And in the denominator, there is Z minus R. So, and it's in the modulus. So obviously this is going to have R over 2. Okay. Plus here, what is going to happen? So this Z is R over 2 plus R. So have I done some mistake somewhere? Let me see the expression, because somehow I think there is some minus plus sign is goofing up. So it should cancel out. Okay, it should cancel out, and therefore you're going to see that basically electric field is going to be 0 here. Okay. No, this is correct. This is correct, actually. So you see here what is going to happen. So sorry for what I said before. This is correct. This is correct. So you substitute here R over 2, and this is R. So what is going to happen here? This is 3R over 2. Am I correct? And this is also 3R over 2. Is it correct?
Yes, sir.
Yes, sir.
Okay. So what is this quantity now?
0.
0. All right. So is it clear now that why electric
Yes,
field is
yes,
going
sir.
to be 0? Very good. So now the second case. So can anybody again guess what could be the thing outside? Do the same thing, do the same thing. So again, let's suppose Z is equal to R. So is that possible? Because if Z is equal to R, you see there is a divergence here, right? This is going to 0 over 0. So this is going to be undefined, all right? So now we have to understand that if Z is greater than R, so what you can take, I mean, you can take R equal to 2, for example, okay? Z equal to 2R. So if I substitute 2R here, then this is going to have 2R minus R divided by 2R minus R. So this is going to again 1. And then again, if I substitute here, then this is also going to be 1, right? So this is simply going to sum up and we're going to get a factor of 2. Is it clear? The statement is clear?
Yes, sir.
Yes, very good. So if I work out on that, we going to get 1 plus 1. And therefore, only a factor of 2 is going to multiply here for any such cases where Z is greater than R. So this is nothing but 4 pi r square, that a spherical shell have a, the surface area is going to give you as a 4 pi r square. And surface area times sigma is nothing but the charge. So you can say that this is 1 over 4 pi epsilon naught q over z square. So we express all our answer in terms of the total charge q on the surface like this. Okay. So is the concept, is the mathematical calculation, everything is clear to everyone?
Yes, sir. Clear.
Very
Yes,
good.
sir.
So I think you don't need to remember it because now you know how to flow the calculations and and these questions, I think in the competitive exams, they generally ask this kind of question, that if you have a cell, then what is going to happen for the electric field if Z is less than R, if greater than R, etc. So these expression is going to give you a very helpful idea. Even one can ask this question like, let's suppose we wanted to find a electric field at distance 2R, or 3R, something like that. Then you just use this expression, and you know that whether it is 3R or 4R or whatever, this is going to give you a factor of 2, So you can always express this in terms of simple understanding that this is nothing but the total charge, because, this is just a charge ball. You can say this is a charge, and we wanted to find, and the electric field expression, very easy, right? So, so these are the special cases, which is really very helpful to understand. Another concept is that for the first case in the inside, we know that inside there is no charge at all. So electric field is going to be 0 automatically, okay? And many other things, we're going to, if when we develop the theories where we have a mirror charges, etc., then you're going to see these concepts more clearly. Okay, so now based on that, now suppose I'll try to have the additional problem in here. Okay, so this is just in the vector form I had expressed as electric field. Okay, now suppose this is a solid sphere. Okay, so this is a solid sphere now, rather than a shell. So now we have to find, with the given uniform volume charge density rho, what could be the electric field. Okay, so now what we can do, obviously we're going to use the previous expressions again, as we did from the discrete to line, line to surface, surface to volume. Okay. So I have just written this, in terms of the words. So again, we can suppose that there are cells here, as in the disk we had seen that we first make it as a ring and then take the infinitesimal dr, and then we calculated, in terms of lambda, and then express sigma in terms of lambda, and therefore, we calculated everything. So similarly here, we can use the previous problem where I can say that this is a shell with a lot of shells, which is interior in this sphere with some radius r, which are going to contribute, and therefore we can integrate over all those expressions which we just got. So the same concept. What we can say here, so let's suppose at inside somewhere, if I take a sphere and we can say that this is a shell, okay, and we can say that this is the dr, okay, and then we assume that the total charge here is given as q int. Int is just like internal, okay, so we can say that total charge interior to this point is given as q int. So ER is the electric field is going to give you 1 over 4 pi epsilon naught q int divided by r square r cap, which we had just shown. Okay. So outside, what is going to happen? Outside, it is very easy. So outside the sphere, all charge is interior, right? And all the charges is given as in terms of saying that this is nothing but the total charge of a sphere is given as q. So you can say that ER is nothing but 1 over 4 pi epsilon naught q over r square r cap. Okay. For the internal again, we have to find that what could be the fraction. So you remember probably in your gravitational field, when you talk about these things, you try to calculate in terms of the density, what could be the gravitational field for the earth kind of system, etc. Okay, considering earth as a sphere. So similar thing we can do here, and we can calculate this internal charge inside the sphere, and for that we know we can just take, because the density is charge density is fixed, it is given as rho. Okay, so we can calculate q and t very easily, which is 4 over 4 pi r cube over 3 divided by 4 pi 3 pi r cube. This is the total charge, so we can take the charge density here, and this is basically given as r cube over r cube times q. Okay, and we're going to express this, use this term in here. Okay, so once we substitute, this ER is going to give you a 1 over 4 pi epsilon naught q over r cube times. So let me explain it one by one, otherwise we will lose the track. What is going to happen if I substitute this value in this expression? So this r cube is basically cancelled with this r square in the denominator, and then it gives us r here. Okay, and obviously this r cube is the constant because this is the radius of sphere, so we can just substitute here. Now we know that r cap is nothing but the r vector. Okay, so this r vector can be written as this. So now you can see the differences, that if you have a spherical charge distribution with a solid sphere, then inside electric field is basically directly proportional to the distance you are talking about. However, if you outside, this is the electric field is given as the basic definition, which is inversely proportional to the square of the distance. So these are some of the interesting things that one should know in the electrostatics. Before I go, are there any question, or is it clear to everyone?
Clear, sir.
Okay, very good. So now, okay, so now the last step. Draw a graph of magnitude of electric field as a function of distance from the center. So how it should look like? Can anybody, give me some idea that how one can draw this? So let's suppose I am trying to have R in this x-axis, I mean the horizontal axis, and vertical is electric field ER. Okay, this is a modulus of electric field, means the magnitude. Okay, so at some point of time, if you start from center, okay, you start from center, you will get up to the radius R. Okay, so let's suppose this is the radius R. Okay, so the question is, I have given enough hint that if you go from 0 to R, how the field should react, and if I go beyond R, how the electric field should behave. Anybody?
Sir, if we go beyond R, then it will be straight line, and from 0 to R, it will be, I think, hyperbolic in nature.
Are you sure? You
Sir,
see here, you see the expression here. Inside the sphere, that means from 0 to R, it is linearly proportional to R. You understand? So this is just an equation of a line. So up to R, you see, this is just going to be like something like this, no? Because these are the constant factor, right? You
yes,
increase
sir,
R.
I thought,
Yeah.
I thought it is outside.
Yeah, no. So similarly, and up beyond R, this is again now proportional to, inversely proportional to R square. So now it is going to be like R square dependence. Okay, so it is something like maybe a parabolic, something like this. Okay, so see, these are very important points which one should notice from the expression itself. So to conclude the today's session, let me give you a very nice idea that how this shell and solid sphere should look like in terms of the the expressions which we learned so far. So sorry. So for shell, if you draw, you know that Z is less than R, electric field is going to be 0. Okay, so it assumes, it simply shows that there is no electric charge inside the shell. Okay, so Ez equal to 0. So if you wanted to draw it up to this radius R, electric field is going to be 0, and then beyond R, when Z is greater than R, what is going to happen? It is simply behave like inversely proportional to the distance square, right? This expression we already calculated, and therefore you can see that this is just like a decaying parabolic kind of thing. Okay, so this is for the shell. However, if it is a sphere, that means the sphere is made up of infinite number of shells from 0 to R. 0 to R means the radius of the shell. Okay, so inside the sphere, since it is directly proportional to the distance, so this is going to simply like a straight line. However, outside the sphere, it is behaving similarly as a shell behaves. Okay, and therefore one can say that this is going to be like a same behavior as it is proportional to, inversely proportional to the R square. Okay, so remember these figures, and with these figures itself, you can always conclude that how easy the problem is. Okay, but to reach this point, we know that there are many mathematics that are involved. So how to reduce this complexity of the problem? So in the next lecture, the next session, we will discuss those divergences and some of the theorems I'm going to use, like from surface charge to volume charge, how it is converted from, linear integral can be converted into surface integral, etc. And we will try to discuss the Gauss law, etc. Okay. So let me conclude the session today. And if you have any question, then I will try to answer the question. Any question? Okay, great. So let me conclude today's session, and see you in the next session, where we will discuss, as I said, various other concepts. And